So I minimize this and I'm gonna now log into Dyrobes. So go ahead and click Dyrobes, launch it, and so this is the home screen that pops up in Dyrobes. Dyrobes is broken down into two components per se. One is the pre-processing or the modeling, and the other is the post-processing. So when we start building the model, we come under the pre-processing approach, and to build a simple shaft, you start with clicking on model, click on data editor. So what it does is it pulls up a window with all the different options on how to model specific aspects of the rotor. So for example, you feed in your units, you feed in your material properties, you develop your shaft elements, you put in some discs. If you want to select some bearings, you can. If you want to add some foundations, you can. So up here we have several other options, and we will be focusing most of our work in this course on these lower tabs here and on this main torsional slash axial tab. So let's get back to the modeling of this example and go ahead and click on the units slash description tab, and what it has here is a display of the units that you'll be using for this particular model and also what the description of this model is. So first thing I like to do is to set my units, and you can see Dyrobes has 4 different unit systems that we can use. One is the classic consistent English units, which is seconds, inches, pound force second square over inch. Engineering English, which is pound force and pound mass being the key differences, and then consistent SI units with meters and kilograms and newtons, and engineering metric units, which replaces meters with millimeters. So depending on what your preference is as far as units go, you can pick either of these options. I personally like to work in consistent English units because that's typically what we use here in the United States. Now in certain cases, when you're dealing with some equipment that is sold in Europe or produced in Europe, then you can go ahead and click on engineering metric units. Now there are some ways of saving your files from metric to consistent English or consistent English back to metric. It's very easy to save back and forth. So for example, if you're sharing models across continents and you wanted to and your preference is working in consistent English while your counterparts in Europe are have preference of working in metrics, then it's very easy to save a Dyrobes file or into a different unit system from the unit system that you started. So without much further ado, I'll go ahead and click on consistent English, and under the description context I'll give it a description. So let's call it example 1, calculating inertia and torsional stiffness of a simple shaft. Alright, and click on save, and it'll open a save as folder window for you, and I will be saving all of my materials on my desktop. So under torsional course materials, example 1, and let's call it example dash 1. Click save, and we're good to go. The next step is to select the material that we'll be using for our particular shaft. So click on the material tab, and you have an option of selecting, looks like 201 materials in this particular model. Now typically some of the more complex models that I've built, I may have at most 8 or 10 materials. For this particular example, let's just select material 1, which will be material number 1, and let's pick typical steel and go ahead and click select. So what it does is it populates this first row, and the mass density that it calculates is 7.32 e to the negative 3, I believe. and it leaves the density. Again, don't forget we're dealing with consistent English units, so we have density in terms of pound force square over inch raised to 4 instead of the classic pound mass over inch cube. And the shear modulus 1.154 e to the 7 psi, pound force over inch squared, and the elastic modulus. And after selecting the material, go ahead and now click on shaft elements. And this here is the meat and potatoes of Dyrobes. This is where you build your rotor. Dyrobes follows a sort of a finite element approach. If you've had any experience modeling using ANSYS, then sort of think about what you do. You select your units, you select your materials, and then you do your pre-processing, build your model, and then you assign your elements. So we're sort of following the same basic approach. And in order to start that, you first develop your element. So in this case, we're only going to need one element, since we're just trying to check the torsional inertia and the torsional stiffness calculated by Dyrobes, and we're then going to go ahead and compare what we calculate with respect to a hand calculation. So without much further ado, under the element column right here, click there and hit element number 1. So this is the first element, so it'll be element number 1. And under sub, click on type in 1 as well. Now what the sub is it's sort of a, for very long rotors, for very big models, it's very useful to use sub elements because it helps with reducing the computation time. In our particular case, since we're building one element, it doesn't matter, so you just keep one sub element. Now under material, type material 1, and I'll explain why you type material 1 in a second. Under level, type 0. Now you type 0 because what the level tab does is it actually gives you a vertical distance. So in this case, since we're building a simple shaft, we're not going to be adding any shaft above the or below the shaft that we're working with, so ignore that and leave that at 0. So our example shaft is going to have a length of 10 inches, and leave the mass ID, which is inside diameter. Since we're modeling a solid shaft, there's no inside diameter, so in this case the mass inside diameter is 0. Now the mass outside diameter, make that 8 inches. Similarly, since there's no inside diameter, there's we leave the stiffness ID as 0, and the stiffness OD, because the diameter of the shaft is 8 inches, the stiffness outside diameter is going to be 8 inches. And then you can leave any comment that you like. So in this case, we'll just call it shaft 1. Okay, so hit save, hit close, save data before exit, click yes, and there you go. This is our first shaft that's been modeled in Dyrobes. Notice up here up top we have example -1, calculating inertia and torsion stiffness of a simple shaft. So what it did here is it pulled the description that we typed in, and secondly, if you go back to shaft elements where it says material 1, this material 1 corresponds to material number 1 that you input earlier. So closing this, close, hit save. This is your first shaft. Now what I'd like us to do is, before we move ahead, I'd like us to carry out a hand calculation of this exact shaft that we've modeled, calculate the torsional inertia, calculate the torsional stiffness. From our hand calculations, I'd like to then compare those numbers with the numbers that Dyrobes calculates, and that'll give you a really good understanding of how to calculate torsional inertia and torsional stiffness. So what I did here is I created a very simple Excel spreadsheet, and what I have are the two formulas, polar inertia and torsional stiffness. So rho is the density of the material, d is the diameter of the material, L is the length of the material. Similarly, G here is the shear modulus of the material. And in our model, we have the diameter set as 8 inches and the length set as 10 inches, right? And the density and the shear modulus, I pulled these out of the values that Dyrobes gave us. So let me show you where we pull them. So if you go back to the Dyrobes and click on model, open data editor, and click on material, there's your mass density, which is in pound for second square over inch to the power 4, and your shear modulus, which is in psi. So I pulled these two values and I pasted them over here, and then I ran this calculation, and what I'm calculating is 2.9474 pound force inch second squared, and the torsional inertia, which is pound inches per radian. So these are the two numbers that we're looking for from Dyrobes to calculate for us. So let's go back to Dyrobes and I'll show you how to calculate this in Dyrobes. So pulling our example 1 module back up, click on model and scroll over to model summary. Now I love the model summary. It's really great because it gives you an exact idea of what parameters you've put in the model, and it gives you all the pertinent information about the model that you need in order to make sure that you have an accurately modeled rotor. So go ahead and click on torsional vibration and it'll pull up this OT0 file. And what it is it's a text file that describes all the different parameters of the shaft that we just modeled in. For example, we have material property number 1, the mass density is this right here, the shear modulus is presented right here. We have one shaft element which is reflected right here, and you can see that we have a length of 10 inches and outer diameter of 8 inches. And so what Dyrobes did, it went in and it calculated your axial stiffness and it calculated in your torsional stiffness, and this number right here is your torsional stiffness. So I'm going to copy this number here and minimize this window and open up Excel, and I'm going to paste it right next to torsional stiffness, and there you go. You have the numbers match. Similarly, going back to the OTO file, we have the polar inertia calculated, so which is right here, and I'm going to copy this number over to compare it with our hand calculations. So copy and open up Excel, and there you go. So that shows you that this is the first, if you will, validation of Dyrobes, and it compares very well with hand calculations. This concludes our first lesson in module number 1. The main point of this module was to introduce you to Dyrobes and to also put some of the theory together with some of the practical application. You know, we typically try to always validate any new software or any tool that we use, and you know, starting off with some hand calculations and then validating with the software starts building your confidence in your modeling capability and also your confidence in the software. So the next lesson I'll be teaching how to calculate torsional natural frequencies and how to calculate mode shapes, and what the meaning of a torsional natural frequency is, what the meaning of a mode shape is, and why they're important to us in torsional vibration. So see you in the next lesson.